Yeah, hello, dear, our distinguished guests, our policymakers, our leaders from academia and industry, and my colleagues. Good morning to you all. It is my pleasure to welcome you to this session on the development framework for national quantum centers, a topic that is central to building sustainable national capacity in quantum science and technology, particularly for us in Ghana. Technologies are moving from foundational research to strategic national assets, and we find ourselves in a form of superposition where today with us we have researchers, educationists, industry, and policy makers coexisting. The challenge before us is to align these elements so that we can evolve into a coherent and impactful national system. While uncertainty is inherent in emerging technologies, it should be viewed as a call for all of us. And we are very honored today to have a professor with us. She is the founder and current director of the Research Center for Quantum Information, Simulation, and Algorithm, which fosters collaboration and entrepreneurship, bringing together academics and industrial partners to develop innovative quantum solutions to tackle otherwise intractable problems and complex phenomena. She has been instrumental in shaping education in quantum science and technology. She designed and implemented a comprehensive suite of quantum computing courses spanning undergraduate, master's, and PhD programs as well. During her tenure as head of physics, Professor Wang also spearheaded the development and successful completion of the Frontier Physics Combined Bachelor and Master's Program, a pioneering initiative designed to attract and nurture top-tier students in cutting-edge physics. She is the well-known lead of the Australian Centre for Quantum Growth, co-founding director of the Australian Quantum Software Network Limited, director of the UWA Palsy Educational Quantum Computing Centre, and a member of the College of Experts for the Australian Research Council. She is also the co-director of Quantum Girls, a government-funded initiative aimed at encouraging girls and young women to pursue careers in quantum science, specifically in quantum computing. We are honored to have with us Professor Jingbo Wang. Prof, please, you are welcome.
Thank you so much for the invitation and for your kind introduction. I hope you can all hear me and see my screen, which I will start. Yeah. Is that okay? Everything is clear?
Yes, please.
Okay. All right. So I will start talking about quantum computing. And in particular, I will focus on the opportunities, but also key challenges. And also I'll touch upon the cybersecurity aspect of it. But before I step into the world of quantum computing and with its promises, challenges, and impact, let's first maybe take a moment to reflect on the incredible journey of computing that has led us to this transformative moment. So I assume most of you have seen this change of computational tools available to us we have actually come a long, long way since the earliest days. Many people believe this abacus dated back to 2500 BC was one of the prototype computer. You can see it has a memory unit where the bits remembers the numbers, and then there is a programming, and which are the rules governing how you move those bits up and down. And then finally, you can read it off of the computational results. And so it has all the essential gradients of our modern computer, memory unit and programmable moves. And then you can erase, you can read off. So nothing happened in the good olden days. Things move really, really slowly. Nothing really changed for thousands of years until the first mechanical machine. And actually, this was around 1832 when Babbage decided to design an automatic machine, which replaced the kind of rules which relies on humans manipulation. So all the rules are built into the gearbox, where you don't have to remember any rules, and you have an input of A and B, and towards the end, it will calculate A plus B, or A take away B, or A multiplied by B. So it was actually considered to be a very ambitious engineering project. And Babbage actually assembled a team and costed him a fortune. And but towards the end, this was actually what was completed, which is only the 1/7 of the original design. Obviously, it didn't work. So then people keep trying, and I think the next milestone was achieved during the World War II, when people actually follow a very different design principle, uh, discovered or devised by Turing. So at that time, I think possibly Turing was looking at those two, and why is very, very complicated. And the hardware does all the computation, the heavy lifting, but didn't work. The machine is very sophisticated and complicated. Where this abacus, as you can see, it's really, really simple, right? And anyone can make it up. The complexity of computing is actually built into the software, the rules, not the hardware. I think that's that's something someone must have noticed, especially Turing. So Turing proposed a Turing machine, which follows the principles of abacus. And he would say as long as this apparatus or physical system can have a memory unit, can manipulate 0 and 1, and that machine, in principle, would be able to do computation of any complexity. And the complexity relies on software, not the hardware. So built upon that design principle, this is the first electronic computer, which relies on the binary encoding of high voltage being 1, low voltage being 0, or current being 1, without current is 0. And so the manipulation is also very, very simple, relies on essentially 3 logical gates: NOT gate, AND gate, OR gate. The complexity will come from the software. So this machine was built And yeah, obviously, looking at this, it's during the World War II, and people believe that helped the Allies to defeat the Nazi. And this computer cost about 1 billion US dollars in today's term. And your mobile phone in your pocket beat this machine in terms of computational power 1 billion times over. And the cost is almost 1 billion times less. So moving fast forward, and this is the kind of computer I use to do research. This is a supercomputer, which has 270,000 CPUs, all assembled together, and that beats our mobile phones 1 billion times over. And this costs about $100 million. So, what's yeah, I'm just trying to say a few. Yeah, okay. So, what does the future holds? This is a roadmap provided by Intel, and as you can see, the computational power really comes from the miniature of transistors, which are the building blocks of computers. So in comparison with the 1945 gigantic machine, which used vacuum tubes and which would be like 10 centimeters across. So it's quite bulky and big. But nowadays, we can make things really in the nanometer, molecular size. I'll just give you a perspective of how small the current computing chips has been made. So this is a flu virus, like COVID virus. And as you can see, it's about 100 times bigger than what we can make nowadays. And we are at the boundary of crossing from the nanometer scale to angstrom. And when we get to the angstrom, it would be the size of a few atoms. And naturally, people would ask what it would be like if we have transistors of the atomic scale. And more importantly, we need to ask ourselves, can we make it even smaller? Can we make our transistors half of the size of an atom? And what would that be like? Therefore, we actually hit a wall. So things is even more complex than just reducing the size. Cross that boundary of nanometers to angstroms, we actually entered into a very, very different world. That word is called a quantum world. And this kind of things are what we're familiar, and we build up our intuition about the world around us. Those are the sun we see rising and setting every day. And at nighttime, we can see some of the stars, the planets, and us, the table, and most of the things we can touch and feel and see belongs to this classical domain. They follow the classical law of physics, and which we actually have a direct intuition built upon from when we grow up, from the baby time and the toddler and go to the school and everything we learn. They behave in certain way, which is not hard to comprehend and understand. But when we cross this boundary, we actually enter a very foreign world where the electrons, atoms, molecules, photons, protons, all those quantum particles live. And it's so different, and to actually have an intuition requires years of study, which is what we call quantum theory. So I'm not sure if you heard about this story in the quantum land. If you have a quantum cat, and that cat can be both alive and dead at the same time. And if you have quantum particles, like the ordinary particles, which we kind of understand, it will be a pinpoint-like object, and it occupy a position or a tiny space at any one time. So if a particle is here, it can't be over there. If I'm here in Australia, I can't be really in Africa. But the quantum particles can be in many places all at the same time. Actually, a quantum particle somehow currently occupy positions both here and in Africa. And we need a very different theory to describe this word, and it's a quantum word. Let's see what we will be able to describe and hopefully make use of those spatial quantum properties to do something otherwise not possible. So quantum computing started way back in 1986, which is 40 years ago now. Wow. So when Richard Feynman, who's a Nobel Prize winner in physics, and he was basically speculating at that time, and he was saying we are going to be even more ridiculous later on and consider bits written on one single atom instead of the current 1 followed by 11 zeros items, so that's billions of items. And he was saying such nonsense is very entertaining to professors like me. So he and a few people around him started to think about this quantum world, how to understand it, and how to build a theory which actually provides the power of control and manipulation, and use that to do computing. So let's just imagine what would it be like if we have those quantum particles. All right. So as I mentioned, the quantum particles include electrons, photons, nucleus, those tiny things. Yeah. And so let's just use electron as an example, because electrons, you can actually measure them, and you can look at, you can control them. You can design an electron gun, for example, and pinpoint some place and somehow deliver the electron to where you want it to be. And if you really want to do that, it's possible. Then we use those particles to represent information. So here, let's say, if the electron is here, we say that represents 0. And if that electron is somewhere else, and it represents 1. And then you make full use of the theory available to us and try to control the 0 and 1, which would give you the information you want towards the end. Okay, so in that way, there is nothing different from classically using the high voltage, low voltage, or the abacus, the bits, the position, or something else. Classically, you can do that as well. Quantum mechanically, you can do it also. So this is a clear 0. This is a clear 1. But quantum world offers us something very special, which is called the superposition. And here, I hope I can explain this well. So So the electron actually is described as a wave function. And that function can be obtained by solving, instead of the Newtonian way, the equation everyone familiar with, which is F equals ma, and we are solving a different set of equations which describes the dynamics and the state of quantum particles. And that equation is called the Schrödinger's equation. Yeah, I don't want to write too many, a lot of maths, but it's just the equation. So by solving that equation, which takes into account the interactions between those particles and also under the environment. So if the environment is a vacuum, it will behave in one way. But if you have electrons placed under some kind of magnetic field, and it will behave very differently. Though all those interactions enters the quantum Schrödinger's equation. By solving the equation, this is what we are going to get. We call it a wave function. And this wave function is, you see, it's bumpy and moves up and down like a wave, like an ocean wave. But the interpretation of those waves is quite different. So the interpretation of those waves represents the likelihood of finding the electron in certain position. So for example, you can see it has a much higher peak here. And we say this is 0. And the other position, we say it's 1. So the interpretation of this is it has information more on the 0 side, but also has a little bit on the 1 side. So mathematically, we write it in this way. Okay. So this is the wave function. We always use psi or phi. And then we know it's quite kind of special. So it's a wave function written in such a way, it has a little bit of 0 and a little bit of 1. So the C are the coefficients, which is a number. And square of that number is the probability of this particle in the 0 state. And the square of this coefficient is the probability of the quantum particle in the 1 state. Now, 1 electron, now we call it not a bit, it's a quantum bit. In short, qubit. So this qubit can be in both 0 and 1 with certain probability. So if you apply the logic gates on such state, so it will do the calculation based on this x. If you calculate fx, so the x is a little bit of 0 and a little bit of 1. Therefore, it will calculate f0 with certain probability and f1 with certain probability. So it calculates 2 numbers at the same time. You may ask, so what? Is there a question? Hello?
No.
Okay. So should I continue?
Yes, please.
Okay. All right. Yeah, please do stop me. And if if I'm going too fast or some concepts I'm not getting cross, this is the fundamentals of quantum computing. Is the most important part. I'll get through. Yeah, in the next few slides. You may ask, so what? Calculating 2 numbers, calculating f0 and f1. F is a function, yeah, right? And classically, we give x a value and we calculate fx. We give x another value, we calculate another fx. We do it one at a time. But it's important to know if we have a quantum computer, it will calculate both f0 and f1 at the same time. If we add another electron, okay, so this is electron 1, this is electron 2, and you can see it will have, so here is 0 and 0. And that would be 0, 1. This would be 1, 0, and this would be 1, 1. In combination, they have a probability because you have a probability to measure the first electron here and the probability to measure the second, the first electron there. And then you can have 0, 0 with a probability, 0, 1 with certain probability, 1, 0, and 1, 1. Now you apply the same kind of logic manipulation, and then you will be able to calculate F00, F01, F10, F11, 4 numbers at the same time. Add another electron. Just imagine there is another electron. All of a sudden, you will be able to calculate 8 numbers at the same time. You calculate 0, 0 all the way to 1, 1, 1. Doubling is very, very powerful. We start from 2, and then we become 4, and we become 8. You possibly all heard of this story, and the king is playing with a chess master and said, okay, what do you want as an award? And the very clever chess player said, I don't want much. I just want you to give 1 grain of rice in the first square and double it and double it and double it. And you can see to occupy the first row, which is 8 squares, it will require 256 grams of rice, which is only a few spoons. But you are going to double and double and double. And in order to fulfill the whole 64 squares, you will require 12,000 words of rice, which no one has. Just imagining we have 64 electrons, which represents 64 qubits. We will be able to calculate that number of F values of that many number of different X all at the same time. That's the power. That's the promised power of a quantum computer. And naturally, people are wondering, is this too good to be true? 64 electrons is nothing. I mean, yes, anything we see and touch are millions and millions of electrons and millions of atoms. But if we can fully control those quantum particles and manipulate them according to our design, and it has a huge amount of computing power, unthinkable. But is this too good to be true? I'm going to talk about another concept, which is about the measurement. All right. So the answer to that question actually is, sadly, it's a yes. It is too good to be true if we do the quantum computing naively. The problem lies in the quantum measurement. I'll describe use this slide. So just imagine we are doing a particular computation. We want to evaluate this F function based on the values of A, B, and C. So here is, instead of just doing plus minus, this is logical manipulation. So A bar means not A. So if A is 0, not A is 1. And this is AND. So A and B have to be both 1 in order to get a 1. Otherwise, it's 0. And this plus is actually the OR. Either of those combinations is 1, it's 1. Otherwise, it's 0. And then you have another AND. So it's just a very straightforward logic computing. And classical computer can do it one at a time. But a quantum computer can do all 8 computations at the same time. So it follows the same classical logic. If everything is, if A, B, and C are all the 0, F will be 0. If A, B, and C are 0, 1, 1, if you do that, yeah, evaluate, you can check the F will have value of 1. Nothing special, except the quantum computer will be able to do all 8 logical manipulations all at the same time. So if you have 64 qubits, each one can be 0 and 1, you will be able to do 18 followed by, I can't remember how many zeros, maybe 20 zeros. That amount of astronomically amount of computing, all at the same time. Classically, of course you can do it. It's the same logic. So, but you have to do it one at a time, one at a time, one at a time. You do 8. And here, yeah, okay. So by after this computing, yeah, you can see coming in and computing, everything is really nicely encoded inside the quantum computer, and the quantum computer knows every single answer. The quantum computer knows 0, 0 will be 0, 0, 1, 1 will be 1, and 1, 1, 0 will be 0. But we don't. What's the use of that? We have to look, we have to measure, we have to obtain the result. And we are classical beings. And we have the measurement is actually an interface between the quantum world, which are the quantum particles, and our measuring device is a classical device, which claps it into the classical world. So this is what's going to happen if we want to measure A, B, C, and F. Okay? Let's say we just measure F. So it can be 0 because you can see, yeah, in this case it's 0, and actually 75% of the time, 3/4 of the time, you will get an answer of 0. But it's possible you will get a 1. And 1/4 of the time, 25% of the time, you'll get a 1. But then the superposition disappeared, and you get only one answer. You don't know which one you will get. All you know, all the quantum theory is going to tell you is about the probability. So it says, okay, try your luck. And 25% of the time you will get 1. If you do this computation millions of times, that prediction is actually precise to the 20th digit. It's going to be absolutely precise. It tells you what you will get, and that's what you will get. But if you only do one calculation, you will randomly get one answer, and you don't know which one you are going to get. So quantum parallelism is not parallel computing per se. It calculates everything in quantum parallel, but only gives you one answer, and you don't even know which one you get. You may ask, okay, yeah, if I don't know randomly, I'll just choose A, B, and C and use a classical calculator. It will give you the answers. So why waste time and money to set up this very dedicated quantum computer? And currently, quantum computer is possibly in billions of dollars in the making. And you get one answer. Yeah. So there is a trick. Okay. So that's why quantum computing is actually very, very different, fundamentally different from the classical way of computing, from the conventional way of computing we are all familiar with. The trick is you don't look, you don't measure. If you don't look, you don't measure, the quantum bits, the qubits, the quantum particles actually live in that parallel multi-possible states in superposition. So if you don't look, you are actually performing the millions, billions, and billions of calculations all at the same time. But you have to be really, really clever to design a process such that when you decide to look, you get the answers you are seeking with a very high probability. And if you could do that, if you can do that, the sky is the limit. So this is one example. And this is the Shor's algorithm, which actually was proposed in 1996, that completely changes the thing. Because before that point, I think you were maybe you were convinced the quantum computer was useless and it does something random, and it won't give you the answer you want. And how to manipulate the probability is a big ask, and it's very, very difficult. And people don't know whether it will be proven, it would be proven to be useful until 1996. Shor came up with this algorithm. Actually, I have a few slides, but it's possibly too mathematical. And you can follow that recipe and count how long it will take for the Shor's algorithm, for the quantum computer to find the two factors of a composite number. What do I mean by composite number? 15 is a composite number. Its factor is 3 and 5 because 3 times 5 is 15. So it's easy. So if the number is small, we can do it. But if the number is a 300-digit number, you can make up those numbers very easily. You just find two very large prime numbers. It doesn't have to be that large. And you multiply them together. Multiplication is easy. You multiply them together, you will get a composite number of a large number of digits. And how to find the factors is so hard because but essentially you have to try one at a time until almost half of that number. So you're giving this number, you said, okay, is that an even number? If it's an even number, one of the factor would be 2. All right. If it's not even, you say whether it can be divided by 3, 5, 7, and so on and so forth. You have to try it one by one. So classically, to find the factors using our current kind of even supercomputer, it will take 150,000 years. And who cares? At that time, you find the factors. But we know because we have a very specific quantum software or quantum numerical recipe, and you can count the number of steps required, and the quantum computer will be able to give it to you within seconds. So the prime numbers of a composite number underpins the current modern cryptography. If a quantum computer can find the factors less than 150,000 years, and nothing will be secret. So all of a sudden, people are starting to pay attention, starting from the banking sectors, the governments, military, defense, and whoever really, really have to protect their data. And they want to be the first to build a quantum computer, not their opponents. So from that point onwards, billions of dollars have been invested in the field of quantum computing. And just to give you a rough idea how vulnerable our current crypto systems. So this is all these are currently used by banks and whoever wants to protect their secret information. And you can see this relies on the integer factorization. It really relies on precisely the two factors of a composite number. And what it will be required will require about 4,000 qubits, 4,000 logical qubits. And I'll talk about what's the difference between logical qubits and the physical qubits in a minute. So you count the required quantum operations in order to break that kind of encryption, it requires about 10 to the power of 11 gates. Okay, and you can see it all. Yeah, if someone has a quantum computer with sufficient number of logical qubits in the thousands and be able to perform 1 followed by 11 zeros number of operations, nothing will be protected. So how far are we from that capability? So I've covered this. This is this slide is a few years old now, and it's published in Nature Physics, and they talk about classical. Yeah, so that's the mechanical machine design and built 1/7 of it around 1933 to the Turing machine. And Turing proposed a set of logical manipulation. You can see it's and or and so on. And he proposed the computer itself should be simple, and the complexity should be in the software. And very quickly, you can see things are happening so quickly. Just a few years, people built the first electronic computer, which occupies a very big room. And I think it has around 1,000 transistors built from the vacuum tubes. And to almost nowadays, and this is a supercomputer stacked and has thousands and thousands of CPUs, and it's a billion times over more powerful than the first electronic computer, and it has capability of 10 to the minus 10 to the power of 16, basically 1 followed by 16. That number is important to remember. So quantum computing also come a long way. And in the 1980s, I talked about Feynman, and there was a lot of quantum physicists, and mostly quantum physicists, theoretical physicists, and contemplating and ask lots of questions about the philosophy, understanding, interpretation of quantum world, and so on and so forth. And the early 1990s, they looked at possible quantum computings and how powerful they are. And around this time, it's the first practically useful quantum software was proposed and verified in small scale. And then in the late 90s and 2000s, people start to build less than a few qubits to demonstrate as a working principle. While when we get into the here, this is only just a few years ago, 6 years ago, Google built a quantum device which has 54 qubits. And this is a very significant milestone because 2 to the power of 56 is 2 times, you do the calculation, 2 times 1 followed by 16 zeros. It's double the capability of the most powerful supercomputer at the time. And that's when Google claimed they have surpassed the classical available computing resource. And just imagine, I mentioned this requires like $100 million to build. If we want to double the computing capability, we have to build another full stack, right? And it will be another 50 to $100 million. But here, to double the capability, we only need to add one single quantum particle. So 55 particles will give you double the amount of available power. So obviously this going to, so the required resource, the cost is going to go exponentially high. But here, it's almost linear. To control 55 electrons would be very similar to control 54 electrons. Not only it provides the required computing power, but it also provides a very green way, an energy efficient way of computing. So because of that work, John Martinez is the leading scientist in that effort to beat classical computer on a very contrived computation. But anyway, even if it's contrived, possibly useless, but it demonstrates its power. Because of that, they received the Nobel Prize, the latest Nobel Prize, together with his PhD supervisor and his colleague. Things has happening really, really fast. So remember that is 2019. A few months later, a Chinese group demonstrated 76 qubits. So we are not just adding 1 qubit every year or 2 years following the Moore's law, but it's a huge jump from 54 to 76, and that's just a few months later. A few more months, IBM is catching up, as you can see, from 54 to 76 to 127. So it's almost double the number of qubits, not just adding a qubit at a time, it's doubling the number of qubits within a year. And you can see a few months later, that number has been doubled almost. Yeah. So I visited this lab, and Josh was my former PhD student, and currently now he's a product manager at this company. When he first joined, this company was a 5-people team or 6, but now it's almost 200. So this is the IBM's roadmap. Actually, all these things I'm putting here has been achieved. Yeah. So yeah, around end of 2024, the qubit number goes into the thousands. And end of last year, it's in the 4,000s. And this is possibly one of the latest. And it's the 6,000 atomic quantum computer built. And if you count, this is actually each dot is a one single atom controlled by the laser fields and manipulated by laser pulses. So I mentioned the requirement of breaking those codes, and it's in the thousands. And now I said, okay, we can now build quantum computer in the thousands of qubits. Are we very, very close to our goal? The answer is no, because there is a significant difference between physical qubits and logical qubits. And to make a story as simple as possible, physical qubits are those real atoms, electrons, photons, nucleus, and because they are physical, the environment will perturb them and introduce error. And quantum particles are quantum devices in general are very delicate. They can be perturbed by the slightest movement or slightest or smallest magnetic field. So one has to build in error correction. So actually, I'm not sure if you ever wondered why our computer the classical computer, like the laptop I'm using to give this talk, it's so reliable, right? You do a calculation and then it gives you certain answers and you repeat it 3 years in the future and it will give you the same answer. While rely on the current or the voltage, which are not stable. It is because there is an error correction model behind the scene. So they use, in general, redundancy check. So instead of just doing one calculation, they do three calculations. And because the error is really, really low, to have two errors happening at the same time is much, much, much unlikely than just have one error. So the three computing, they take the majority vote. Any computing in between, they just take the majority vote. So if two of the three gives you a zero value, while the other one is one, you just assume it's zero. So error correction in a classical sense has been done, and it's not that hard. You just do, yeah, three more times of computing. But in the quantum case, it's very, very hard. I don't have time to explain why you can't copy a quantum state. You can't copy a single qubit. And there was a famous saying, you can clone a lamb, yeah, but you can't clone a quantum qubit, a quantum bit. So the error correction is much more complex. And when people talking about useful quantum computing, you have to assume you have to. Otherwise, the whole thing just decohere and the information will be lost in the noise. You get nothing. However, if you can do quantum error correction and fully, you don't have to think about the physical properties. You don't have to worry about the error. A logical qubit is equivalent to a precisely designed abstract qubit behaves ideally as we want them to be. We need 4,000 of those. Before April last year, April 2024, so before April 2024, no one has made even a single logical qubit because it's extremely, extremely hard. So this is April 2024. Together with Microsoft, Quantinuum is currently a leading quantum computing company, a spin-off from Cambridge University. And currently, if you check, that company is valued about $10 billion. So they are leading in many ways. Most importantly, they are leading in making logical qubits. So this is the first time they actually demonstrated, instead of using a single qubit, they use a bunch of qubits and made 4 logical qubits. And they demonstrated those logical qubits behaves almost like ideal qubits. We can regard those as logical qubits. So that is April 2024.
Sorry, I would like to ask a question, if you don't mind.
Absolutely. Go ahead.
Wait, just this slide talking about putting theory into practice. I'm just, I want to find out, I mean, for the past years before 2024, was it just theory we were just talking about that made it look like it was so real? And it's just in 2024 that we could say that the whole thing was real. I mean, looking at what they did.
That's a great question. That's a great question. Yeah. If you want to do precise computation, and yeah, because some computations you can get a rough answer, right? And that's still useful. but certain computations, like to find the factors of a big composite number, it has to be so precise. And the two factors will be the one you are after. Otherwise, it will give you random thing. So like if I want to find the factors of 15, I need it to be 3 and 5. But it might, yeah, if my computing is not precise enough, and I can do the analysis, I know it will give me 4 and maybe 6. It's not useful because 4 and 6 are not the factors. But some computation is less demanding. I can use an example of optimization. Yeah. So let's say you have a vehicle routing problem. So you have the supply chain. You want to design a particular pathway of delivering goods. All right. So yeah. So to find the best possible solution will require absolute precise computation. But I don't really mind if the solution is not the best. If it's close to the best, it will save me millions of dollars. I was told, yeah, like the ports around the world, every decision they make is actually the cost will be in the millions if they make a good judgment and a bad judgment. Yeah. So if I can save $1 million of close to the best solution, or I have to try to find the best solution to save me $2 million. I think the $1 million solution is still worthwhile, which doesn't require absolute precise computing. If I might answer your question. So before April 2024, and when Google demonstrate a particular computation, they can do it much quicker. And that they were using a very noisy kind of qubits. Does that kind of answer your question? What I really want to say is putting theory into practice and a quantum computer with noise are still useful.
Okay. All right. Thank you.
Yeah, okay. But we want to do the best we can. Therefore, we rely, for example, if we want to design drugs and so on, if we really want to do something really serious, and we rely on our quantum computer to give the correct answer, and then every step has to be right. And then we have to have logical qubits even for that simple example of finding factors. And I know I did a simulation. If I have lots of error, it won't give me the factors that I need to break the code. Yeah. Okay, let me continue. I think I'm taking more time, um, but I'm going to finish soon. Yeah. So, so actually, my research group now have access to this really wonderful quantum computer. And do I have, okay. Yeah, so I'm about to talk about another, yeah, this is really recent. This is just 1 or 2 months ago. April 2024, they demonstrated for the first time a working device with 4 logical qubits. Now they claim they have achieved 48. I have not read their papers. They are going to publish the papers in Nature or Science, and people can really check and so yeah. But I have not. This is just their claim. So now with a new design, they can deliver 48 error-corrected logical qubits. So you can see the development from nothing to 2 to 4, and then a huge jump. And we don't know what's around the corner. So I think this is this is the state of the art. Investment in 2025. And this is, many believe this is estimation on the very low end, because even I look at the investment from Australia, one company, Psi Quantum, received funds in just one single private company received 1 billion, which is 1,000 million, more than this, from the federal government and the state government of Queensland. So I think you could easily say the global effort in 2025 is around $100 billion. So the real question everyone need to ask, not just physicists, not just computer scientists, how should we strategically position ourselves for this transformative technology in computing while addressing the significant cybersecurity risks posed by quantum computer? Are we ready? No, we are not ready. Can we afford not to look into this? No, we can't. And because even if your opponent company or industry have access to this power, you don't, it's game over. It's possibly like that. So this is my group, and I think the picture is kind of like old and taken a year ago. And we also experiencing exponential growth. And this year, I possibly will have 10 new PhD students. I received 12 scholarships, and just a matter of who is going to take them. So we are supported by many people across and in the community, and we're working with many of them at the same time. And we are looking at a wide range of practical applications. I'll stop here and answer questions.
All right, thank you so much. That was a very wonderful and interesting presentation. Please, any questions?
Yeah, I'm showing this quickly. It's my team and divided into 10 theme groups. And we are doing, very high level mathematics. And we are solving ODE, PDE, SDE, and so on. And we're working with people on the real quantum computers. We do optimization, we do signal and image processing, and quantum machine learning, and bioinformatics, and finance, and medicine, and so on and so forth. So we are quite ambitious, and we have big goals for this year.
That's great. Yeah, so maybe before we waiting on others to ask a question, I would like to ask, considering Ghana, I mean, we are just starting. If you have any advice or suggestion in terms of the framework for National Quantum Center in Ghana, where or would you suggest we start from in terms of the hardware parts? I guess we are not ready. Are we ready? But then what would be your suggestion or advice?
That's that's a hard question to answer, because mainly because I don't know the ecosystem and in any sectors in Ghana. Therefore, it's hard to address and to maybe come up with any suggestions also. Maybe I have a few slides I would like to share before I have to go about what we are doing in Australia. Maybe there's some lessons we can share. Yeah. So let me find my other slides. Okay.
Please, if you have questions, you can ask.
Okay. So can you see my slides?
Yes.
Okay. Yeah. So this is prepared by someone else and kindly shared with me. Uh, so we actually about 2 years ago now, a little bit over 1 year, we received about I'm just trying to think about 18 to 19 million dollars from the federal government of Australia to form this Australian Centre for Quantum Growth. In short, we call it Quantum Australia. So this Quantum Australia is a consortium of 13 universities, 13 leading universities in Australia. And on top of that, $18.8 million we received from the federal government. Each university actually chipped in. I think altogether it's about 25 or $26 million. And also the state government, each state in Australia also chipped in. Yeah, which includes the New South Wales, the Queensland, Western Australia, and, uh, and so on and so forth, you can see. We also have industry partners and startup companies, all kind of chipped in and help. So it's a quite big consortium. So what we are doing is to build up this what we call a quantum consumers journey. So our aim is to establish and maintain a quantum ecosystem, and which leads to translation accelerator. So you can see we are covering a whole spectrum, start from people, industry, and government departments and public, and not really engaged. They don't, yeah, many of them have only heard this buzzword quantum, but don't know really what they are. So we offer outreach programs, workshops, hackathon, and so on to bring people in so they can watch and learn. They come to attend conference and events and assess material we prepared and undergo a certain kind of training. And hopefully that will bring them one step further to participate and develop strategies within their industry. And like they can sponsor us and build relationships and carry out R&D and so on and so forth. And really engaging, looking at how quantum can transform. So here, when I talk about quantum, it's not just quantum computing. It also includes quantum communication and quantum sensing and the related possible applications. And then we want to, yeah, build a quantum country. And yeah, I think we believe quantum technology will underpin the modern world for decades to come. So that's kind of our lesson. And so we have programs. One, the main focus is the ecosystem development, and we want to build up the partnership. And we also have the new ventures and try to encourage, create, support startups, provide mentorship, provide funding pathways, provide industry connections to help innovators to launch, scale, and hopefully succeed. So this is supporting each other at like a circle. Yeah, so the new ventures program and allocate resource to help people to start, and then they will build up this community and then form partnership, and that fits back in. So this is in 2030, And we are hoping Australia is going to be recognized as a leader of the global quantum industry, and quantum technology are integral to a prosperous, fair, and inclusive Australia. And there are certain initiatives, and we organize industry workshops. We have quantum meets finance, quantum meets logistics, quantum meets medicine, quantum meets, so we have theme workshops to help any particular industry to build up their capability. And then we want it to be inclusive. In particular, we want to elevate quantum women's voice and try to engage women, and which is still very much lacking in any STEAM disciplines. We want to be able to elevate that voice. And we do outreach and in particular focus on the next generation. So we go to school and have public events as well. And so every year we'll organize a Quantum Australia conference. This year we'll be in Adelaide and in April. So if anyone wants to come, please do let me know and I'll see how we can help. Yep, that's the end. So I hope that helps. I hope that answers a little bit of your question.
Yeah, thank you. Please, any question from anyone?
If not, I have to go. I
All
have
right.
I have a very early morning meeting, and thank you so much for changing the time. Otherwise, I would not be able to do this. Thank you.
Thank you as well. But then maybe before you go, we can take a group picture if you don't mind. Please, let's take a group picture. If you don't mind, you can put your camera on. Please, can you stop sharing your screen for us so that's
Yep. Okay.
okay, please, are we ready? Anyone showing his video? If not, then I'm just taking the picture. You can give us that quantum smile. Okay. Anyone else joining? Okay, last shot. Okay, someone is joining. Okay, all right, go for it. Then I'm taking the last one. All right, thank you so much, Prof. Thank you so much for your presentation. And
Thank
dear
you.
all, thank you so much for your time as well. I know we inconvenienced you today, but you made it possible to join us. So thank you and have a very great day. See you next time.
Yeah.
Bye.
Bye for now.
Well, hello. Hello, Bro Martin. Yeah, yeah. Traffic event. Picture the party is near Baham. Oh, all right. Sometimes we are co-reading. Oh, I am. Charlie, what's up? Charlie, I'm a Davi. Ove si avranno, numero eh, guys, sì, obi any in contact and obi any from the door. Last time campaign, we get my get it again, Michelle. Run like a long packet, only a Che sei quando? Bẹ́ẹ̀ náà fi bẹ́ẹ̀ fẹ́ẹ́lì ní kẹ́lẹ́ sọ̀pọ̀. Là, c'est même pas que tu peux la loi, fi, aí, no mas é bom, não é que não ia igual. Mas é só quando você na pior. Hum, hum, hum. É, o wife. Bẹ́ẹ̀ náà kàbú tí ẹ nínú ìwà fi wá. Se é prática pura, alô, ele é prática pura. Ah, o menu yẹn lẹ́nu kà fẹ́rẹ̀ bẹ́ẹ̀. Ah, ah, se bẹ́ẹ̀ gbogbo rẹ̀ kẹ́ o use 24 volt ní mic. Ah, mi like 24. Hum, o